Hello students, welcome back. Let's go to section 3, the final topic of lesson 6a. And this topic can get really bad really quickly. So let's draw a line somewhere. And I'm going to draw a line on geometric examples mostly. Modeling, so we are talking about some complicated word problems, but I don't want to go too deeply into this. Something that you can see and do geometrically. That's where I'm going to draw the line. Please stop the playback and read through the problem. There are a lot to read. Okay, do you see what's going on here? Red car is moving and yellow car is moving, and you have to tell me how the distance between the two is growing. We have a lot of other pictures here, but this picture gives you too much information. So that's not really good. My suggestion is to simplify and produce much easier diagram, much simpler diagram. And then things are going to be easier from this point on. Sorry about this typo. Diagram M is missing here. Okay. Instead of that, how do you like this? I don't have anything except the red car here, center of the intersection, and the yellow car there. Now the red car is moving 40 miles per hour, isn't it? Yeah, 40 miles per hour, that's the coefficient. Yellow car is moving in 30 miles per hour. So 40t, 30t, okay, and the growth of the distance there as a function of t. Good luck. Once you get this picture, it's easy from this point on. You can use Pythagorean theorem. Getting this diagram, of course, that's going to be the hard part. Look at the picture and go through the problem. 40 miles per hour, 30 miles per hour. Okay, here's the answer key. Pythagorean. All right, so much for the first problem. Next, another geometry problem. Again, this picture has too much information. And this too is going to be Pythagorean, as a matter of fact, if you read carefully. Let's see. We have to connect this box here to this household over there. And we have two options. One is along the road, and then second is underground. Underground cabling is going to be more expensive. So we have two different coefficients, $500 per mile versus $700 per mile. Which is which? Read through the problem and figure it out. Well, did you stop the playback and read through the problem? Not yet? Go ahead and do that. All right, I'll assume you're ready. So again, let's simplify this picture. This picture has too much information, like all these trees and stream, they're totally unnecessary. Basically, this is a kind of picture we want. 5 miles, 2 miles, and then horizontally along the road, x miles, and then underground, y miles. Now, if you have this x and y, can you figure out the cost? 500 miles along the road, 700 miles off the road or underground. So which is x and which is y, and how do you get the cost? Well, here's the answer. 500x plus 700y. Does it make sense? 500 along the road, 700 off the road with appropriate color coding. So this is 500x, that's, okay, 500x, 700y, that's the cost that you want. And then as for which is which, Oh, never mind. Which is which, that's gonna be, and that's gonna be too much. We'll just simplify this, solving one variable with respect to the other using this geometry, and eliminate one of the characters. And I can eliminate y because we have a right triangle, so using x and these numbers, you can solve for y. And once you do that and plug it over here, then you're going to get function of x only. So what is it? Stop the playback and try to do it on your own. Again, Pythagorean theorem, that's going to be useful because we have right triangle forming here and y is hypotenuse. Did you get it? Here we go. Pythagorean. Hypotenuse squared is horizontal squared versus vertical squared. And the vertical squared is 2 squared. Horizontal is this one. 5 minus x. So square root of that, that's going to go over here. And if you do that, we have the function expression. 500x, the blue part, along the road. 700y, off the road. So 500x, along the road. 700 times the square root, that's off the road on the ground. And there's a function. Now, as for minimizing this cost using calculus, that's not what we are up to. If you do it right, you're going to end up with somewhere around here, pretty close to 3. Not precisely 3, but darn near close to 3 miles. And that's going to be the best way to do this cost minimizing method. Okay. The final example, another geometry. This geometry is going to be 3D geometry, but believe me, it's going to be easier than previous problem. So, what is this? Stop the playback and read through the problem. So, we have this cardboard, or what is this material? Okay, cardboard. And then we'll have to cut those corners off and then create this open top box, okay? And we want to find out the volume here. So what is the volume? Base area times height. And base area is going to be area of the square down here in the center. And then these are 4 sides. So if you fold those up, the height will be x. Do you see that? So this distance is x. All those distances x. So fold it up. Then height will be x. So what is the volume? Okay, here's the answer. 24 minus 2, 24 minus 2x, 24, and then here's x, another x. So the one side is 24 minus 2x. And then that's square, so that's in squared, that's base area. And height is, of course, x, we discussed it. So that's the volume. And you can simplify this if you want to by breaking off the parentheses and doing all those. And this is a function you get, a cubic function. If you draw the graph, yeah, you can use Grapher to do that, and you're going to get something like this. And if you want to maximize the volume, you get somewhere around here. Around x equals to 4. That's when we have maximum volume. Precisely what is it using calculus? That's not something we are going to do here. Up to expressing it as a function and graphing, that's something we can handle. Let's see. No, this part is calculus, so we won't do it. Okay, so much for this problem too. So we went through some modeling problems, and that's where I'm going to stop. Modeling problems can get really rough really quickly, so I'm not going to go too deeply into these. Also, we are going to get a little bit more important modeling problems in the next lesson, linear modeling and quadratic modeling, so I'm not going to overemphasize here. Up to this much, okay, that's where I'm going to stop. Thank you.